4.8 quadratic formula, a little bit more stuff. Okay, so in a previous lesson we talked about dropping stuff, and dropping stuff is really fun. We even had an equation for it. It was the height of the object is equal to negative 16 t squared plus h sub naught, where negative 16, acceleration due to gravity in feet per second squared. Okay, now we're going to launch stuff, and that's even more fun than dropping stuff. You know this. Okay, so that equation is h is equal to negative 16t squared plus v sub 0, or v sub naught, t plus h sub 0. So the h sub 0, initial height, v sub 0 is our initial velocity. Because whenever I go to throw something or launch something or whatever, I need to have some sort of starting speed. Okay? So, look at the pictures down below. That first one, if it has an upward velocity, it's going to be positive. If I'm launching something downwards, its initial velocity is going to be negative. So this is kind of why this negative 16 t squared, that acceleration due to gravity, is negative, because we're going downwards here. And then if it's just horizontal, our initial velocity is going to be 0. So some of those things keep in mind whenever we're writing our equations. Okay, so here's the first one. No, take that back. Here's just a more general equation. So this one right here, this negative 16t squared, that was whenever it's in feet per second squared. Okay, so that's because g is equal to 32 feet per second squared, at least here on Earth. And then if it's in meters, because sometimes people like to have it in meters rather than feet, g is equal to 9.8 meters per second squared. Okay, so just depending on what units that you're talking about. So that's what that g is right there. And that g, well, if it's not on Earth, it could be any place else, like maybe the moon. And whatever its acceleration due to gravity, we can use the same exact equation. So speaking of that, how about an astronaut standing on the surface of the Earth's moon throws a rock vertically into space? Right? You go to the moon, what's the first thing you want to do? Throw something. Okay, so how long is it going to take that rock to hit the moon's surface if the rock is thrown at an initial velocity of 40 feet per second at a height of 5 feet, and the acceleration due to gravity on the moon is 4.3 feet per second squared? So I don't have enough room to write here, so here's all this stuff written out for me. So I need to write my equation. Height of my object is equal to, it's a negative g, so negative 5.3 over 2 t squared. Now, is my velocity going to be positive or negative? Well, I'm throwing it upwards, so it's going to be positive. Positive 40 t, and then I'm starting at an initial height of 5. So there's my quadratic equation. And we want to know how long is it going to take for it to be on the ground. So if we're talking about it being on the ground, that means my h is got to be equal to 0 if it's going to be on the ground. So I just put a 0 in there. Now I can use the quadratic formula in order to solve it. Now I'm going to go ahead and write the steps out here, but I'm going to put it in the calculator because you can see I'm going to have some messy numbers here. Let me just go ahead and divide this out here. I got negative 5.3 divided by 2, negative 265. Alright, so I'm going to rewrite this equation. 0 equals negative 2.65 t squared plus 40t plus 5. Put it all in my equation for quadratic formula. It's negative b, so negative 40, plus or minus square root b squared. And b squared, that's 40 squared. I can do that one because it's 4, and that'd be 1600. Minus 4 times negative 2.65, that's a, times c, which is 5, all over 2a, so negative 2.65. Alright, Now when we're putting this into the calculator, you got to be really, really careful. Got to have all kinds of parentheses. Also, this is plus or minus. You can only put one in at a time. Put the plus one in first, do the minus one second. Okay, so let's start off with a set of parentheses with negative 40. Let's do the plus one first, and then the square root. Inside the square root, now if you have the old calculator, it opens up parentheses. This one's the newer operating system. I don't have to do that. 1600 minus 4 times a, which was negative 2.65 times c, which is 5. Okay, I need to get out of this and then close the parentheses on the whole top. Divided by, now since that bottom has some multiplication in it, I'm going to have to open up some parentheses on that. 2 times negative 2.65. Close those parentheses. Here's our first answer. Negative 0.12 seconds. T equals negative 0.12 seconds. That doesn't even sound reasonable. So in other words, it hit the ground before I even threw it. Crazy. Alright, let's try the other one. So instead of having to retype that in, I'm just going to hit second entry, scroll over to the beginning of this thing, change that plus sign to a minus sign, hit enter again. That's a little bit more reasonable. We've got about 15.2 seconds. And there we go. So let me make this have a little bit more sense here. The reason why you get one of these answers is negative 0.12 seconds before you threw it is because of this. Say this is a graph of the thing. We're starting at 5 feet. And he throws it, comes back, hits the ground, and this number right here is 15.2. If we were to trace this part back and finish off the parabola where it would touch the ground in some negative time is negative 0.12 seconds. And so that's where that other answer comes from that doesn't make much sense. Alright, so here's one for you to try. Same kind of deal, except for now we're talking about it's on Earth. So I'm going to use that 32 feet per second squared. All the other stuff's exactly the same. Go ahead and pause it. Come back and see me, see if you got your answer right. Alright, so you're back. Trying to figure out how long that rock's going to take to hit the ground back here on Earth. All the variables were the same, all the parameters were the same except for the acceleration due to gravity. Now it's 32. So whenever I put that 32 into the equation, it becomes 16. So my equation is h equals negative 16t squared. The reason why is because it's that g over 2. Alright, negative g over 2. Plus 40t plus 5. I'll put all those numbers A, B, and C into the quadratic formula. Probably use the calculator. Crunch them numbers. And I get t equals negative 0.12 seconds. I've got to throw that one away because that doesn't make any sense. And then the other one, t equals 2.62 seconds. Now you don't have to draw the little picture here, but this is just making sense of it. The one that does make sense is 2.62 seconds roundabout. And then the other one's negative. That's what you would get if you were to complete that parabola back there past the x-axis, past 0. Okay, so last question on this. Compare your answers from part A and B, the one from the Earth, the one from the Moon. What can be said about gravity on Earth compared to the gravity on the Moon? Well, that question's actually pretty easy. So the time it took for that rock to hit the ground was 2.62 seconds, almost 3 seconds. Over here on the Moon, it took a little bit over 15 seconds. Obviously, gravity's way stronger on the Earth than it is on the Moon. Now, I probably could have gotten that by just looking at that 5.3 feet per second squared versus this 32 feet per second squared. So the answer on this one is very simple. Gravity on Earth. So Earth's gravity greater than Moon's gravity. Moon. Yikes. think I can spell that word correctly. Moon. Alright, that concludes Objective 1 in a 4.8 quadratic formula. So we derived the quadratic formula, came up with it ourselves using the completing the square method, and then used that quadratic formula to solve any quadratic equation. Sometimes I'm just doing it without the calculator so I can get an exact answer. Other times the numbers are just so crazy I have to put it all in the calculator. Make sure you're paying attention where all those parentheses go. Okay, I'll see you in Objective 2.